Hello, and welcome to IoT Builders, a live stream where we discuss a range of topics on the Internet of Things, from embedded devices to cloud services, all from an IoT Builder perspective. It is April 26, and this is episode 26 of our weekly live stream. My name is Alina, and I'm a senior developer advocate in the AWS IoT service team, and I am joined here today by my colleague Nenad. Hi, Nenad. How are you doing?
Hi everyone. Yeah, I'm doing good. Thanks once again for being your co-host here at IoT Builders. So I'm Nenad Ilic, senior developer advocate for AWS IoT, as you might all know me as of now. Yeah, looking forward to today's discussion.
Yeah, nice to have you, Nanat. And today is going to be a really interesting session. We are going to discuss topics like observability and the very edge, so observability at the very edge for FreeRTOS devices. And we are joined today by Johan Kraft from Percepio. Hi, Johan.
Hello. Thank you for having me.
Thank you for being here with us today. Could you introduce yourself briefly for our audience today, and tell us a bit about you and about Percepio?
Yeah. So I'm the founder of Percepio, a company based in Sweden. I'm the CTO and are working a lot with products and technology roadmap. We are very much focused on observability for RTOS-based systems and also Linux, and are offering two solutions in that space. One is Tracealyzer for recording software behavior locally at the locally connected device, and then we have a solution for observability in the field in deployed devices called DevAlert, which is more of a cloud service.
This sounds super interesting. Of course, we're going to get into what observability is and why it is challenging, because I'm really curious about that, and I know our viewers are also curious about that. But let's start with how Percepio got started. So, what is the history there?
Yeah, well, this started actually some 20 years ago now. I was hired as a contractor / industrial PhD student at a company called ABB Robotics. And they're one of the leading vendors in industrial robotics and have a very advanced software control system for their robot arms. Several million lines of code. And I was working there like 2003, 2005, somewhere around there, on helping them improve the observability of their software, basically a RTOS-based control system, but with connections to other systems, etc. And they actually started using that solution in production, so it was included in all delivered robots for many years. And we could see that they had a huge benefits from that, because they could solve the problem. They could access diagnostics remotely and solve problems at home on their desk instead of having to fly over engineers for troubleshooting. And back in those days, there were no AWS IoT core and things like that, modern secure services. They were using like a GSM modem, I think, and they dialed up the robots, and then they could collect diagnostics in case a customer reported an issue. So of course that was rather primitive, but today you have much more interesting possibilities, and can get alerts in real time, basically, and by leveraging more modern, secure connectivity frameworks like MQTT, etc. But yeah, after that, I started Percepio to basically be able to focus on my ideas around observability, and we started offering Tracealyzer for FreeRTOS around 2010. and we have somewhere around 250 active customers on that at the moment. It's used in everything from like toy projects to fighter jets. Everywhere you have an Artlas basically. And later on, when we saw what the kind of the promise of IoT was starting to become with free Artlas in AWS, etc., and with the inspiration from the ABB robotics use case, we started to design this DevAlert solution, which I'm going to show you today.
Okay, yeah, that's really interesting. So quite some history there from early stages. So about observability, I think a lot of people or a lot of developers think that maybe observability is just a big buzzword. Could you, tell us what you think observability is and how you think it's useful and where you think the real challenges when it comes to this are?
Yeah, I mean, yes, there is a lot of focus on observability now because systems are becoming increasingly complex, and then you need better observability. I think the definition of observability is your ability to understand the inner workings of a system based on the outputs. And there are numerous solutions for that for cloud workloads. I mean, you have a lot of services out there, and AWS also have plenty of offerings. But edge devices are quite different. I mean, to start with, they are, by definition, at the very edge. They are exposed to the uncertainty of the physical world. People are touching them and doing things to them, and they are exposed to cyber threats in a different way because people can actually touch the systems and plug in a cable, stick in a USB device. But they're also rather different from a software perspective. These are, if you take, for example, an IoT sensor, it's typically not running Linux because that's too expensive. It's running something like an Artlas, like free Artlas, often on a microcontroller, a device that has maybe 1 megabyte of storage and a few hundred kilobytes of RAM. And these devices are, I mean, a processor like a microcontroller is only a few dollars, maybe $1 in some cases. And the hardware security is also very limited on those devices. I mean, in many cases, you have a flat address space where any thread can do anything to the whole system if something goes wrong. So in comparison, I mean, in a Linux system, you have process isolation, address randomization, and things like that that are protecting the different parts from each other. That is possible on IoT and edge devices as well, but not really in the same way. And it's not always enabled. So the point is, edge devices have in many ways just as much need for observability as cloud workloads, but historically they have had a very poor observability. I mean, if you take a classic embedded system, it's like a black box. Then you could, of course, add connectivity and maybe get some sensor data up in the cloud, but you can see the numbers, what the sensor is reporting, maybe what the temperature is, but you don't really, if there is some kind of anomaly, maybe the sensor is reporting the wrong number, it's really hard to know why that is.
Right.
And that's obviously one important use case for observability and edge devices, to be able to analyze issues, to do basically remote debugging. If something is obviously wrong, but then you also have the whole space of kind of cyber threat, cyber security use cases. If there is some weirdness, some anomaly in your system, was that a bug or some accidental issue? Or is it something more serious that you really need to look into ASAP?
Yeah, so I think it's because the devices are also not next to you, right? They're not in your lab somewhere where you have access to them and you can, investigate more. I think remote debugging definitely becomes more and more important. So of course, having tools in place that facilitate, getting traces, understanding how the software operates, understanding how the operating system works, if anything is wrong, becomes really important. So, yeah. Sorry, go ahead, Johan.
No, please go ahead. I was confirming you.
Yeah. So, I mean, what I was trying to get to is, maybe for your audience, if you can explain to us what traces are and how they, what they achieve and how they help.
Yeah.
With observability.
So traces is kind of an overloaded term, can mean many things depending on the situation. But typically it's basically a form of logging. You can get your software to report what it's doing. In the simplest form, you add prints in your code that are showing you what's happening. But you can do that in a more systematic way by having more efficient binary logging in APIs and in kernels, and get streams of events that show you what's going on in the software. If I can share my screen, I can show you how it could appear. The beauty with tracing is that since the information is kind of structured into known events, it's possible to do analysis and visualize the data. And that can look like this, for example. So here we have our tool Tracealyzer showing a FreeRTOS system. My screen resolution is a bit bad right now, but what we see here are different threads in a FreeRTOS system from a microcontroller device, where it could also be an IoT device, edge device. So we can see how they are interacting, how they're using different APIs, different FreeRTOS APIs in this case. So we can see that threads are synchronizing and sending data to each other, etc., messages. And we can see how they are scheduled. This green task here, for example, is activated up here, but then it's not running until the higher priority tasks have completed. Because in an RTOS, you typically have fixed priority scheduling, meaning that if there are higher priority tasks ready to run, they always have priority. And that can actually cause a lot of software issues like priority inversions, deadlocks, and things like that. So when developing RTOS-based edge devices, you are much more, you have much more control over the scheduling compared to like on a Linux machine, for example. But you also have a greater responsibility for ensuring that the parameters are right. So there are more things that can go wrong. But basically you get the timeline of the software execution like this. So this time goes downwards here, and you see each swim lane here shows a different task or thread. Could also be interrupt handlers. And you can see other higher level visualizations like this, showing the CPU load of the trace, for example. So we can see how much each task or thread is running at any particular time. This way you can see anomalies. For example, why is this task running so much here? Then we can zoom in and see more details. So Tracealyzer is mainly used as a kind of system level debugging tool, but it can also be used to analyze the software design and see that the implementation matches the intended design, and to analyze timing and performance issues. You can use it either directly with a debug probe and stream data over a JTAG interface or local Ethernet connection. But you can also actually use that Tracealyzer within the scope of DevAlert and look at traces from the field. And that's essentially how ABB Robotics were using Tracealyzer quite many years ago already, but they had a very a rather primitive solution for getting the data.
I was about to ask this. So, I mean, when you're having like a GDB or JTAG, and
Yeah.
then, you can get that data and then start plotting. But this is what really interesting, what you said is like, you can actually do this once those devices are in the field, right?
Yeah, exactly.
That is
And
amazing. That's amazing.
one thing that people are asking then is, what isn't this generating a lot of data? Yes, in a way it is, because a data stream like this it can be thousands of events per second. But if you have, and that can be viable with a local connection, it's maybe 100 kilobytes per second or something like that. But you don't want your battery powered IoT device or your costly IoT connectivity to feed that kind of data. I mean, it would lead to a lot of costs, and most of the data will be kind of sunny weather. Everything is fine anyway. So what we have done instead is to have a kind of edge aggregation. So we buffer this data in a ring buffer on the target in the device. And whenever there is an issue, if we notice that something went wrong, we can provide the most recent 1,000 events or so, a few kilobytes of data. So normally our solution is actually silent. It doesn't send anything to the cloud. Only when a problem is detected by the device, then a few kilobytes is sent. So it's quite efficient. And it's not only about traces. We can actually provide other kinds of diagnostic data from devices nowadays. We have just added support for things like GDB crash dumps, so you can actually get a very detailed dump from your device, like a core dump, so you can see the stack trace, the call stack of the current task when the issue was detected. But that's not in Tracealyzer, but this is actually in another part of the solution. Should we move right on to the DevAlert demo, and I can show you a bit how it works? Or
I think that sounds really good. I mean, I think it would be interesting because you mentioned that data is being sent to the cloud. It would be interesting to see how.
So I will
this
give you
happens.
a brief hands-on demo now. I have these
Excellent.
two ST boards that I have prepared for this. So they have a firmware program that is probably the worst firmware in the world, because the only thing they do is to fail. And the point is to demonstrate how we report issues, failures, or anomalies. So when I plug them in, I have my trusty power bank here with two USB cables connected just for power. So what will happen when I plug in here is that they will boot up, connect to my Wi-Fi, and then connect to AWS IoT Core. You can see the LED here. When there are two LEDs lit, then it's connected. And then when it goes back to one LED, then it has actually failed and is restarting. And at this point, it's actually sending alerts to AWS or to our DevAlert service. And let's plug in the other one just to get a little fleet of two devices. So I
Nice.
have to put these aside. So they will actually start feeding alerts to an S3 bucket in a separate AWS account. And if we open DevAlert here, we can now see some alerts coming in. The red ones are the ones that are recent, the ones within 5 minutes. And what we see here is the issue overview, on the dashboard. This is basically an aggregated view of. I mean, here we have perhaps several hundred different reports here, but they are grouped by the symptoms or the fingerprint of the issue. So we see the top level classification of the issue here that's provided by the device. We can see all the details if we open here. So we see how the the different symptoms. This is basically what is classifying the alerts, and this is provided from the edge device when the issue is reported. So we see the location of the issue in the device source code, the current task or thread is running, the file and line, and the stack pointer. These are actually hash codes because we want numerical symptoms. So the symptoms is basically how we aggregate the information and how so they are grouped. And we can see the statistics here on a high level, basically what's going on in our fleet. We can disconnect these now, but now we have collected a bunch of alerts. I mean, this could be from the other side of the world, but right now they happen to be near my computer. But the interesting thing is what we can do with this data, because what we see here is just a summary. But if we open the details here, we can see 2 links. And this one is a trace for Tracealyzer. Let's open that to see how that looks. We can also see an error message here. This tool that's opening now, it's something called DevAlert Dispatcher, and I will explain that more later. But it's basically a downloader and a launcher in a way. It is our solution to do this kind of to provide this diagnostic data in a way that is ensures data privacy. Because the data isn't actually coming from the DevAlert service, but from a separate storage that can be managed by the customer. Anyway, so here we have a trace from this from one of the boards just a minute ago, and we can see what things happened, and we can see that it failed because it tried to allocate too much memory. That's perhaps not super exciting, but we can have a look at we can see the line here that it's tried to allocate memory in main.c line 973. Okay, that is probably a stupid mistake, but if we look
this is pretty
here,
cool you can actually go jump and then inspect exactly the line of code. That's amazing.
Yeah, and we can actually get more, because here we have a crash dump for GDB. If I click this, I download part of the memory contents that were stored.
You can see the stack trace and all that stuff. Or?
Like this. So this is a GDB server that opens up on my local computer, but it's showing this data from the remote device.
Nice.
So here we can see where the problem was detected, and the call stack and fault status registers. That's not really relevant in this case, but if there's a hard fault exception, then you can see more details there. And here you can see all the registers, etc. And this is actually an interactive GDB console, so you can actually type commands here. I don't really know GDB commands by heart, so I can't use them. But, if you do, you can use this. But if you are more of a kind of IDE-oriented developer like I am, you can actually use, for example, Eclipse to load this crash dump. So I have a special debug configuration here where I can load this into Eclipse and see it like this. So here we can see that we had this application failed hook here. For some reason, this is showing on the wrong line. I think that, it's probably just some...
Yeah, the code gets updated and then probably jump.
Yeah,
but this is pretty cool. But is it possible to have like a live connection to the device and actually kind of go step-by-step debugging, or is it just like
this is kind of a snapshot. So you get the DevAlert solution is actually one way, and that's actually intentional for security reasons.
Yeah, makes sense.
So it's only sending like a small packet, and we can receive it on the other end, and we organize it and we make it available. You can of course implement another channel back, for example, using device shadows. You can control this, for example, enable it and disable it remotely. But DevAlert itself is one way.
That makes sense.
Yeah,
But we
that
have
makes sense.
some other examples here you can use this for things like search or fame like that. But we also have one example that I think is extra interesting, and that is you can actually use this to detect stack corruption, which is typically what happens if you have a buffer overflow issue. And buffer overflows are really dangerous because they can be used to inject code into your system and allow for remote code execution. So here we can actually see there is some demo code here that is intentionally causing a buffer overrun. But we simulate basically that we get a network message, and it is there is a problem, and it's writing too much data into a buffer, and then there is an error handler that kicks in. For transparency, I should say that this is actually a feature in GCC we're using to detect Stack Overflow, but it fits very well with DevAlert to report these kinds of issues. And in this crash dump that we have downloaded now, we actually have the modified stack contents. So that can actually be used for a forensics triage to analyze if this was a kind of accidental bug, or if someone injected actually an engineered exploit to try to manipulate the stack.
You can figure out which packet it was, what was the content, I guess. As
if
you
you
said,
if you open this in the debugger, you can actually use the memory view, and then you can have a look at the stack contents and see if it looks like ARM instructions or if it's just some string from another part of the application.
Nice.
Cool. So that's DevAlert. You can integrate this in many ways. We have designed it we used AWS IoT Core and MQTT as a kind of reference integration. But also have a setup where you can upload from a plain serial port. So you plug in a USB cable to your laptop, and then you can get the data that way. And that way you can actually use this without having an AWS connection working. For example, if you're having connectivity problems, you can actually download this locally, and then we have a script to upload the data to the DevAlert service. So you still have everything collected here, because I believe this dashboard and the cloud access is really important, because it enables a team to kind of access the same data and see the same picture.
So Johan, can you tell us a bit more about the data? So where is, if the data is stored in the cloud, where is the data stored?
Sure. Let me show you this picture. This is a high-level overview of how DevAlert works. So up here, it basically starts here that you specify an alert in the device software. So the device builder is free to define their own alerts. I mean, typically you have a handful of error handlers in your code. Maybe if a malloc call fails, you have a central error handler for that, at least in FreeRTOS. You have hard fault handlers, and there could be special fault handlers for example, for stack corruption. So by adding like instrumentation with DevAlert on basically a handful of places, you can catch a lot of different issues and anomalies. And these are reported to the DFM library. That's the DevAlert client, basically. This is a passive library. It's not running in the background in any way, apart from if you're using Tracealyzer with it, then we are hooking into event hooks in FreeRTOS, for example, to collect information. But that's actually driven by FreeRTOS. But anyway, the DFM is basically just an encoder. This library encodes a diagnostic packet that can be uploaded in any way you like to what we call the device backend, which is basically typically an AWS account of the device builder. So all the yellow parts here is controlled by the user of DevAlert. And the diagnostic payloads actually remain here in the device backend, the AWS account that would normally be used by the device. So this is just like any other uploaded IoT data, basically. But a small amount of information, basically a reference to this data, is sent to the DevAlert service, including the symptoms that are provided here in the reporting, but not the diagnostic data like the crash dump, memory dump, and traces and things. That remains here for privacy. And that's really nice because the customer can maintain control of this part and can configure the storage as they see fit without having to rely on Percepio for that. And DevAlert provides this dashboard with special links. And these links trigger the dispatcher tool that you saw briefly in the past. That's actually triggered as a protocol handler that kicks in when you click on these links. And this has previously been configured to get the data from your special storage. So this is, for example, accessing an S3 bucket with your login, with your credentials, and downloads the trace or the crash dump you have selected, and then it fires up the right tool or some script to view the data, for example, in Tracealyzer or in a GDP debugger, or perhaps you have other kind of data. You can actually add any kind of data you like here. You can provide, do an alert and provide like a Word document if you like, and then open it in Office. But I mean, to be serious, I mean, you can actually use this for ML ops, for example. If your ML inference would be uncertain in some case, you could actually provide the raw data as a payload in DevAlert and have a custom tool in the other end to analyze it.
Yeah, it's pretty interesting. And even so, in scenarios that I guess you don't have that kind of like MQTT connection, and you have like some persistent storage, you can technically store that, and then just export it manually. I guess will that work as well?
Sorry, I didn't quite follow. How do you mean?
Yeah, so I mean, here you have like this FreeRTOS application with the DFN library, but in scenarios that this MQTT connection is not available, at the end of the day, the data need to land in S3 bucket. So if you don't want to send the data, but you need to debug at some point, you can save this to storage and then export it manually to S3. And
we have, for example, as I mentioned, we have a way to upload the data over a serial connection to your host computer, and then that can upload it to the S3 bucket. Or you can actually store it in internal flash. Maybe there's just a kind of temporary connectivity problem, and it can be uploaded later.
I see. And is it possible to create your own alerts if you're interested in doing so?
Yeah, definitely. That's actually how we see that this is used. We have some examples that we recommend, like you should have alerts in hard fault handlers and maybe if an assert statement fails. But it's very much possible to, or advised actually, to be inventive and see where really think through what would I want to know about. I mean, for example, if you have a network stack and you have say that you have a switch statement to handle different types of incoming packets, and then you have a default case where you go if the packet isn't recognized, or maybe you have some error handling if some sanity check fails, then it can make quite a lot of sense to report anomalous incoming data, for example. It could also be, say that you are noticing, if you're monitoring the CPU load in the system and you're noticing that it's much higher than it used to be, maybe that could be seen as an anomaly that could be reported. So you can actually use DevAlert to build your own observability, basically. It's very flexible in that way.
Yeah, so I think this possibility of building your own alerts together with the possibility of bringing more data in, if you need more data that helps you analyze, I think this makes it really powerful. Um, so maybe could you tell us some of the use cases that your customers are using DevAlert for?
Mm. We see quite a lot of requests for where people want to use this. I mean, the first step is often that people want to use this in internal testing, not to test DevAlert as such, but to let DevAlert monitor their system tests or in field testing. And if you're doing kind of system testing in a lab, you could actually use the serial port upload, because then you can easily plug in a serial cable. The device is stationary and sits next to another computer. And the benefit of that is you can actually use it on any device, independent if it has AWS connection or not, or cloud connection or not, even kind of old school isolated embedded systems. But you can still leverage the cloud by uploading the alerts that are collected that way. And then we see that the big value of this comes when you deploy a product with this integrated. This is in some way a design-in solution, because it can basically help you de-risk product launches and over there software updates. We have customers saying that in the past they've had kind of a chaotic situations with lots of bugs in deployment and people complaining, and they don't have no idea what the problem is. It's the customer can't explain it. They just say that the device is beeping and restarting. And I mean, for the builder team, the development organization, it's like all hands on deck for months to try to figure out the problem, and that way they lose customers, they lose business, and it can be a real threat to a product team and then the business around it. And speaking of threats, you have the whole security threat situation with IoT devices, edge devices being kind of a new attack surface in many cases. There is a kind of a funny story actually. I read a report a few years back about a US casino that was hacked by a compromised aquarium fish tank pump control system. So they had this big aquarium in the casino with an advanced control system that was connected to the cloud somehow, or to some, at least to some network. And for some reason, this was accessed somehow, compromised, and they used that as an entry point to the rest of the casino network. And the attackers actually managed to download 10 gigabytes of data from the casino network over a period of several months. Imagine if you could capture a thing like that within seconds, or even within milliseconds, if you notice that something weird is going on in your device. I mean, the average cost of a data breach is something like $4 million. I'm not sure how they came up with that number, but I mean, obviously it's something bad and expensive, right?
Yes, not trivial.
Of course.
And that's something people are really scared about. So that's also something we can do with DevAlert. Well, it doesn't detect things like that for you, but it's an enabler that can help you report strangeness and anomalies in your system. You still have to figure out a bit what to look for and what to detect, but there are some kind of ideas for that in the business. I mean, for example, I know that AWS Device Defender have some monitoring of CPU load, for example. That's a good thing to look at. What we can do with DevAlert is also to provide traces and crash dumps and more details when there is an anomaly. for example.
Yeah, I mean, this should be a standard part of the standard infrastructure for any IoT devices in general.
Yeah,
I mean, as you mentioned, it's really important to, get to know your devices and how they're performing in order to prevent anything. So it makes sense.
right. So I can mention also, I think the next slide is a bit relevant. This basically explains what the aggregation in the developed service, this blue part here. And why is, I mean, we have a database there that takes care of this metadata, basically sorts it based on the symptoms. And the symptoms can actually be defined by the user. And the point of this is, I mean, you don't want this huge log of thousands and thousands of alerts from all sorts of devices about various things, because it becomes really hard to kind of see what is new and important compared to issues you have seen many times before. So the point of this aggregation is basically to filter out the things that are new and highlight things like this. So instead of showing you this long list where you have to basically inspect the details of each one to understand what it's about, you can actually get this high level to-do list basically. And if something new pops up, it would appear here on the top basically, and you can have a look at one or two examples of that. You don't have to analyze each and every report.
Nice.
Because they should be similar or identical. And I mean, this way we believe this is important. One part of the design requirements or design goals with DevAlert is scalability. That is all about the amount of data we can process. We have built on scalable AWS services, so we can handle large amounts of data without problems. But it's also about the kind of perception. How can I, as a user, work with this in an effective way, despite having thousands of alerts coming in over lunch? That's also a kind of an aspect of scalability, that you can cope with the data that is handled. And I believe this is an important part of that solution, to have this overview.
Nice. And how do you connect? I'm wondering now from the overview perspective, is like, how do you connect this with a specific device or a group of devices? Do you have that view as well?
Yeah, you can see this in if you right now, this is actually a bit too abstract. We're changing this overview. So you'll be able to get more columns showing the device that reported the issue, etc. This information is available. You can see this under details.
Nice.
But right now the dashboard is actually showing. I get some static in my speaker. Do you hear that too?
Yeah, we hear it.
Okay, right. So here, this alert key is basically the identifier of a certain alert. And this part here, this is actually the device ID.
Nice.
And in this case, we're using the processor serial number for that. And that is combined with a unique session ID. And so you have a unique stamp or a unique identifier for each alert. Right.
So one,
yeah.
I do have a question. I mean, the dashboards look really nice. I would be curious, and of course we can do this a little later as well. I would be curious to see how this library is integrated at application level in the application code on the device. But maybe we can, if we finish with the dashboard first, maybe we can talk about that after.
Yeah, I can actually show you. It's fairly simple. Let's see. Oh, I better open up my IDE for this. I'm using an older development tool called System Workbench for STM32. It's a bit slow. That was what was provided with this ST board.
I remember this one. Yeah, so it's based on Eclipse, right? So I remember.
Yeah, it's not
It's
the most updated version.
the funny days of each vendor has had its own IDE that was based on Eclipse.
Yeah,
So
I'm feeling more and more inclined to just start using VS Code and things like that instead. Right. Eclipse is always an interesting story, but I've learned a lot about Eclipse when developing this recent demo, actually. You learn it the hard way.
yes, exactly.
Yeah.
Right, so let me show you some
Mhm.
glimpses of this demo code. This is actually available on my GitHub page. It's still maybe a bit beta status, but this particular project, that is. But if we look how the DFM library is found down here under here, so it's a couple of files. It's not, I think it's about 1,500 lines of code or something. It's not huge at all. And this includes, we are relying on another open source component for creating the crash dumps. That is actually including a hard fault handler. So you define this when you include you define this as your hard fault handler, basically,
Oh,
and
nice.
other fault handlers. So this is catching it for you, those kinds of issues. In other cases, you can use. Let's look in our FreeRTOS config.h here. Here we can actually see two kinds of integration. We have the assert statements here. So this
I see.
statement is used in many places, both in FreeRTOS and in libraries and other places, to do sanity checks and see if something is wrong, if the parameters are valid. And here we're using a macro called DFM trap to
Yeah.
provide basically a crash dump or stack trace and tracealizer trace whenever this happens, whenever it fails. So this integration is basically one line of code.
It's really interesting how this changes the paradigm of embedded software development for like constrained devices and microcontrollers. You should, I mean, back in the days, it was like you should avoid putting asserts, you should avoid using heap, all that kind of stuff. But now it's like seems that it's good to start using more and more asserts because you have that tooling that allows you to kind of debug this even when devices are out in the field and you have all this.
Yeah, I mean, asserts have traditionally been used mainly in the development phase to
Yeah,
help you catch errors early, and then you remove them in production
exactly.
because they have a certain cost in terms of flash
Exactly.
size, etc. But
Right.
it's quite, I mean, you have to compare that cost then to the cost and the hours needed and the customer impact of having, if you don't catch issues as soon as possible, if you miss some issue, maybe you have some kind of stack corruption that is causing weird symptoms in other places in the code. You really want to catch issues as soon as possible and get the most amount of information with it to be able to fix it ASAP. So I mean, this is all you need to hook in DevAlert on assert statements, basically. We can also have, I mean, printfs can be added to the tracealizer trace, so you can see those. And down here is how we are basically hooking in the trace recorder into FreeRTOS. So this is providing the trace macro definitions.
Okay.
Yeah.
So it's like
And
three things. Sorry, go on.
Yeah,
no
there is
need. Go for
probably
it.
a bit more to it, but
Yeah.
it's integrating DevAlert DFM is a bit more job than to just integrate tracealizer, but it's not that much. I mean, it's not a huge project. What I was thinking about something else. Yeah, we have the DFM library has two different kinds of kind of interface modules for making interfaces, for example, cloud ports. So a cloud port is basically how we are uploading to how we are outputting the data. So here we have, this is basically just a C file and the header file. So we have one here for AWS IoT Core and one for serial upload. And then we also have something called a storage port, which is about how you save, if you're not connected at the time, maybe you are crashed, you need to restart, then you can write the data to internal flash or some other storage and restart. And this is showing, this is the implementation for writing to STM32 flash. Right, so yeah, so if you want to try this, I will be happy to answer any questions, of course, but you can actually, I will soon publish this, or it's actually already published, but you can find this on my GitHub page. My user is called Johan Kraft, but this will also be available on the Percepio GitHub page soon. So github.com/Percepio is where we normally put stuff. Right now, this is at Johan Kraft. So here it is. It's still a bit, I may need to polish this a bit more, especially the instructions, but I think it's fairly well documented now. But you can actually use Develop without writing any embedded code if you like. We have this sandbox solution. If you go to Percepio, I can start at percepio.com, Develop, then you have this information here about the Develop sandbox. And this actually runs a QEMU simulation of an STM32 device in the cloud. So you can run this pre-configured demo right away. It shows you a graphical interface with an elevator, and you can kind of generate errors there. You can log in to, from here you can actually log into, you go to develop.io. If I log out here, you can actually sign up for free evaluation, and then you can access the sandbox and get started. So if you have any, if you find this interesting, you can learn more at percepio.com/develop. And you can always reach out to me or others in the team if you have questions or comments or ideas. I'm really curious to learn, to hear what you think.
Sounds really interesting.
Yeah, this is really good. So for the developers who are watching us, we pasted a few of the links that Johan has mentioned. So you can use the GitHub. So you can go to github.com/Percepio/repositories. You also can access the DevAlert, via the Percepio website. You can sign up for DevAlert, and you can access the sandbox. You can try the elevator application, and generate some errors and have a look at that. And if you have any questions, then of course you can reach out to Johan, or you can reach out to Johan via us, or however you prefer. And this has been really super interesting. So I'm, and I think Nenad as well, we find observability in the IoT ecosystem very interesting. And the solution that Percepio has via Tracealyzer and via DevAlert is for sure something very interesting for the developer community out there. So thank you very much, Johan, for participating with us today and showing us all this interesting stuff and doing the demo, which has also been really interesting.
Well, thank you for having me. It's been a pleasure.
Always a pleasure to have you on our show. And also as a recommendation for the developers out there who have not watched the episode from the Embedded World conference in Nuremberg, we had Johan and Mike as well from Percepio, and they also gave an overview of Tracealyzer and DevAlert. That episode is also accessible via our IoT Builders channel, of course, in the live stream section. So do watch all those episodes from Embedded World 2023. because you will find a lot of interesting information on observability, security, functional safety, and a lot of other details. Any last words, Johan?
Oh, that's a tough one. Well, as mentioned, I have this STM32 demo project on GitHub now. I will keep polishing that for a bit more and make sure to post that on the Percepio GitHub page soon. But we will, of course, provide this for other boards as well in the coming months. We have basically made after the big updates of DevAlert some month ago with this new support for crash dumps, etc. We are kind of restarting the demo work and making new demos because it's much more interesting now, I think.
Mm-hmm. Oh, and one thing that we found out from Embedded World, or at least that was new to me, is that you are now supporting state machines as well, right?
Yes, we are. That's actually a part in Tracealyzer, but it can of course be used within DevAlert as well. So as part of this Tracealyzer trace, you can log state transitions if you have either some software state variable or variables, or maybe some hardware state you're interested in. You can trace those transitions and see both a state diagram visually in Tracealyzer and a timeline, much like a logic analyzer view.
Pretty cool.
That was included in the Tracealyzer 4.7 release in March, I believe.
Mm-hmm.
Nice.
Super interesting. So yeah, I mean, I think happy hacking to everyone who wants to try this out and have a look. Any last words from you, Nenad?
No, I think this was pretty cool. I mean, looking at the FreeRTOS code and then how this is packaged, shipped to the cloud, and analyzed with all those graphs, it reminds me of old days with GDB debugging and all that stuff. So this is pretty cool. But now on a high, big scale of fleet debugging, amazing stuff.
Mm. Yeah, I mean, I think for such a complex problem, these two solutions definitely make it seem very simple.
Yeah.
So this is good.
I think that's actually quite interesting. I mean, the DevAlert has a fairly advanced design, but when you use it, it doesn't show. Just click on a link and then you get the data. And I mean, that's how it's supposed to be. But there's a lot of kind of complexity behind that that doesn't really show when you demo it.
Nice.
Yeah. This is what is all about developer experience. So good developer experience definitely makes a huge difference when using libraries and when trying to problem solve. So yeah, this has been really nice. And of course, we are kind of running into our last 1 minute of the show. I just want to thank Johan again for being with us here today, and of course, thank you, Nenad, as well for co-hosting the session today. Do reach out to us if you have any questions. Do reach out to Johan if you have any questions. And otherwise, of course, we will see you in IoT Builders next Wednesday at the exact same time, where we're going to have, again, interesting conversations with a surprise guest. So stay tuned with us for next time. And yeah, thank you very much, everyone.
Thanks,
Thank
everybody.
you. Bye.
Thank you. Bye.